So hello everyone, this is week 9 of the course Transport Phenomena of Non-Newtonian Fluids, and in this particular week, this is week 9. So in this particular week we will be particularly looking at heat transfer. So the first lecture which was dealt with in the following week was this the flow of the transfer, this temperature distribution in fully developed flow for any Newtonian fluids in the tube, right? And then we started some discussion about if there is this reactive system, so how the transport phenomena and everything will be dealt with, and at the end we had this transpiration cooling. So this particular week we will be discussing that. So let me just project my screen. Okay, so this is screen there. So the contents that you have already show my screen in. Okay, so admit. So like in this particular week we will be starting with how a fluid which is flowing through a tube, for example, the fluid is flowing through the tube and the flow is fully developed flow. So in that case, how the profiles, the temperature distribution you are going to get for the Newtonian fluids, right? And then again we will be starting with the governing equations, and along with that the boundary conditions. The main thing, if you look at the slides, then what you will observe is that gradually the difficulty level of entire course is going towards inclusion of different other transport phenomena. For example, you started with this initially only the flow of the fluid, right? So only the momentum transfer was happening in that case, and in that limit you observed that this that time you was not bothering about the temperature distribution or the energy balance or the concentration or species balance, right? But now in this particular course, if the same problem that we had, the flow of the fluid in pipe, right? So that time we have done it with this power law model, and in the power law model, if you put that index n equals to 1, then you are anyway reducing that equation to the Newtonian, right? But what will happen if the entire analysis is done with the temperature distribution intact, right? So now what will be happening is this velocity distribution will be there, that was anyway, and stress distribution is there also, right? But now this inlet temperature is different as compared to the outlet temperature. So you are having some temperature at the inlet from where the fluid is being flown, and because of that there will be transport of the energy also along with transport of momentum, right? So whether the how the temperature profile will be coming up into in this particular scenario, that will be that has been the key part of this particular lecture. So again you started with the assumptions. So this Newtonian fluid with the constant physical property, and why Newtonian you have considered right now, just to ease out the calculative steps, and to basically appreciate what are the steps that you will be following to simplify the entire system. Because even without the temperature, we have seen that for the power law model, the equations that we were dealing with were tedious. In this entire course, what is needed is you have to be having control on what are the steps you have to do, what is the entire procedure, how you are going to analyze your do the analysis of your system or the phenomena that you are observing, right? So the second point is steady, so there is no transient changes with the within your system. Laminar flow, incompressible, and non-isothermal flows, right? So here it is not isothermal. Lastly we had this to be isothermal, right? So fully developed flow, we are saying no gravity, no reaction, no viscous distribution. So following these assumptions and these related question can be asked in the assignments that you are getting, and then in the final examinations that you will be facing anyway, right? So flow is in z direction as a function of r. So we have seen that this direction they have defined as z, and the radially across the radius is r, and then uh, temperature is function of both r and z. So you know that the velocity is function of r, right? But you don't know about the temperature for the time being, whether the temperature is function of r or whether the temperature is going to changing with the r and with the z too, right? So that's what it is. The temperature is function of r and z both. So the boundary condition that you are having at the center r is 0, there you are having finite temperature, some finite temperature which is coming and getting convected because of this inlet, and then at wall r equals to capital R, and there is a constant heat flux, and at the inlet z equals to 0, t equals to t1. So this cross section you are having temperature t1, and here you are having some other temperature. uh, so again, let me just see if things are okay. Yes, we are. Yes, I am connected. So if you see, let me just project my screen, right? So the problem uh, is the first problem that will be the part of this particular week is transport temperature. Okay, some problem. Let me just fix this. Temperature distribution. Let me just have my. Let's just set it in a way that we can see the screen also, right? Okay, so this temperature, just fix it. Yes. So the temperature distribution of fully developed by Newtonian fluid in a tube, right? Okay. Then second was this temperature distribution with reaction. Distribution with reaction, right? And the third is this transpiration cooling, right? So what is this transpiration cooling? If anybody knows, just what is this transpiration cooling? Hmm? What is this transpiration cooling? Just think about this. The thing that sir has showed in the class. It is mostly used for the nuclear reactors. There is one fluid which is flown, which helps in cooling down, and sometimes the porous media is also there in order to have some uh, overall mixing, and then temperature maintenance, thermal maintenance. Hmm. So that we will be looking at, but just to tell you main points about this transpiration cooling is these are very important. uh, if Let me just put it here like this. So this Transpiration cooling is, I will be just setting up the definition first. So transpiration cooling. It is a advanced thermodynamic technique. Okay, advanced thermodynamic dynamic technique, right? It is used to protect structure from extreme heat. Used to protect structures from extreme heat, right? By moving a coolant. Sometimes this coolant we fluid, air, or something else. There will be coolant, right? So, so from where the coolant is moving, sometimes these coolants are liquid or gas, and they are moving through the wall of that structure. So this is structure's wall. So through the wall of the structure, you are having this movement. Okay, and sometimes via the porous materials or porous material. Layer of fluid at the surface, which further reduce heat flux from the environment to the structure, right? So how it works is a coolant, usually nitrogen, air, or water, is forced through the microscopic pores in the wall of the structure. Afterwards, as the coolant passes through, it absorbs heat from the solid matrix and may evaporate further, boosting cooling power via latent heat effects, right? So the main point to know here is that the latent heat effects, right? So the latent heat effects, we just yeah, here the latent heat effects, right? The coolant exiting the outer surface forms a thin film that drives hot incoming air away, thermal drawing effect, reducing heat transfer to surface even more, right? So the applications like jet engines, nuclear reactor applications are aerospace, jet engine, nuclear reactor, right? So these are some of the ways that it is used. So that's what I wanted you to just give a feel, because in the lecture we had the most of the theoretical and derivation kind of thing related to transpiration cooling, but the real use, the real principle, and then the what type of coolants are there in that problem that was discussed, and then where this application, this finds its application, we have discussed here. So these you can expect these also as a part of your curriculum, and it can be asked in the exams, right? So if you see, so let me just put it here like this. Yes, so this, where is this? Yes, so let's increase it. Yes, so you start with the continuity equation again. So del rho by del t plus 1 by r del by del r, rho r v r plus 1 by r del by del theta rho v theta plus del by del z rho vz, right? So that is the thing. If you look at, you are having this steady state, so first term is going to be 0, right? So this del by del t is 0, and then you are having z direction velocity, so vr is 0, v theta is 0, and then it is fully developed flow, so this is also 0. So continuity equation is defined. It's like continuity equation is satisfied, right? So r component of the equation of motion you are having. So these equations you are just taking it from the standard books, and you are using these equation for your analysis, right? So you don't have to memorize these equations because these are available, and in exams if it is there, you will be provided with the equations, like you are given the in the questions also, what you may have seen your assignment. These are provided to you. Just the concepts are needed, how these equations come up into the picture. So the physical understanding of the system and what is happening with the system, and where the different modes of transport phenomena are taking playing their role, is crucial as far as this course is concerned, right? So so these all steps were similar, like we had done it in our previous lectures. So you found that this del p by del z is pl minus p0 by l, and then again through the r momentum, you had this del p by del z to be this, right? Now uh, these uh, this is not a function of r and theta. Okay, so as per that, you can separately solve this right hand side and left hand side accordingly, and you had this for this p del p by del z, you obtained it this one, and then based on that, the vz comes out to be this, right? So at r equals to 0, vz is maximum, thus c1 should be 0. Okay, so because at r equals to 0, this is not finite. Okay, so this has to be 0. C1 has to be 0 to have the finite velocity, right? So that's why C1 should be 0. So now you are having C1, and at r equals to capital R, your velocity is 0. Then accordingly you will get C2 to be minus of minus del P by L r square by 4, right? So this r square by 4 mu, if you look at and you see, then the expression for the velocity profile comes out to be vz equals to minus delta p by l r square by 4 mu 1 minus r square by r square. So it is similar to what you have in the regular pipe flows, which is Vmax 1 minus r square by r square, right? So now, for a fully developed Newtonian flow in a finite long cylinder, you had this. Okay, then energy equation, you are having this one. So if you remember these terms, convective terms coming up into the picture, taking care of the thermal energy flow because of Vr, V theta, and Vz, and then transient term, and then this is coming because of the thermal conductivity. So diffusive heat transport uh, in different direction, r, theta, and z, and then mu theta phi v is coming because of the viscous dissipation, and then now if you look at this, then all the different terms are going to 0 except vz, right? So you are having rho cp vz del t by del z equals to k, and this side you see it is fully developed flow. There is no variation of temperature in theta. So you had this understanding, right? So this only r and z you are having some variation of temperature. So that's why it is a r and z. Right? So now the heat conduction in z direction is very less, right? As compared to conducting conduction in r direction, right? So that's why this term is very less, right? This term is very less, so you can put it to be 0, and accordingly you are having this, right? Rho Cp Vz del T by del Z equals to 1 by R del by del R del T by del R, right? So just have just look at this. What is the different thing that you are going to do? So we are now having the revision of first lecture of this week 9. So these weekly sessions are meant to give you a recap of what all things you have learned in the entire week, and then I will be solving some 10 questions or more than that uh, around the topic, and similar question you will be asked in your weekly assignments and in your this examination most probably, right? Most of the questions that comes will be conceptual, so you need to have the basic understanding, and in many places you have observed that these lots of dimensional and non-dimensional terms are coming up into the picture. So what are the physical meaning of those dimensional and non-dimensional terms, and how those non-dimensional and non-dimensional terms are getting uh, related to this the phenomena that is happening. Suppose it is pipe flow, or suppose heat transfer through a sphere, or transfer through a sphere, right? Or this transpiration cooling in these kind of scenario. So in the transpiration cooling, you have seen that the air is blown, it is passing the inner cylinder, right? The inner sphere, and then going to the um, intermittent layer, and then passing to the outer sphere, and then cooling the entire system in this way, right? So let's see. So this equation comes up, right? You just put this for this expression for Vz that we have already defined, and then this comes out to be Vz is Vz max 1 minus r square by r square, right? Del t by del z equals to k by r del by del r del t by del r. ठीक? Okay. So now you know that this expression. Let me just uh, show you if something is there. Let me just put it here. Okay, so if you see here, this conditions that you are having, okay. So your velocity profile is any parabolic, right? And your shear stress profile is right. But you don't know about this. This is tau. This is u. But you don't know about this z. It is r. You don't know about the velocity, about the profile of this temperature distribution, right? Because just you know that at r equals to 0, there's some temperature here. You had this T1 temperature at this interval, so T is finite, right? And at r equals to capital R, you know that this whatever del T by del R will be there, it will be constant. Okay, and then at z equals to 0, you are having t equals to t1, right? So these are three boundary conditions you have. And what equation you are going to solve is the equation that we are dealing with, is this one, where you can easily see that this is rho Cp Vz max, right? 1 minus r square divided by r square, del t by del z equals to k by r del by del r, r del t by del r, right? in this one you see there is this temperature variation because of R, there is this temperature variation because of Z, right? And at different Z you are having temperature, so only at the inlet you are having temperature. So if you see here, uh, these these non-dimensionalization is employed in order to do this, because to ease out rule out some factors, and then and how this scaling comes up, you just have to rearrange this particular expression and get this scaling, right? So the theta, which is temperature, is non-dimensionalized T, right? We just write T minus T1 divided by Q0 R by thermal conductivity, right? And then this non-dimensional number corresponding to zeta is R is zeta, and for this Z, Z divided by rho Cp cap Vz max, right? So it is okay. Now if you see, once you convert all the dimensional uh, boundary condition to the non-dimensional one, and you just have to follow the steps that are here, is asymptotic solutions you have to go for, right? And then this entire expression is converted into this one, right? You see, and then the asymptotic solution that you are going to solve is like asymptotic solution can be possible for large value of this zeta, large value of this Z, value of Z. Large value of zeta means large value of Z, right? Large value of this. This is zeta, this is beta. What I'm saying is, okay. And then if the large value of Z is there, then this non-dimensional factor will be high. And after fluid is sufficiently far downstream from the beginning of heated section, one expects that the constant heat flux through the wall will result in the rise of the fluid temperature, which is linear in this non-dimensional Z quantity, right? So that's why they had this basis, and then they have the derived it also, and they also expect that shape of the temperature profile as a function of radial non-dimensional parameter will ultimately not undergo further change with the increasing z, means the zeta, right? Hence, reasonable quantity, is a reasonable solution for this large value of zeta is following this theta 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 zeta equals to this C0 zeta plus psi theta, right? So if you see this, so with Z, so this reasonable solution for the large value of this Z, when it is large, it is mostly depending on this one only, and then this is constant C0, and it has to be determined. So you have to determine it. Now we should check whether this form of the solution, which is 9, is satisfied all conditions. So at zeta 0, zeta equals to finite, right? So you are having zeta is 0, you have to see this, and then boundary condition 2 is at 1, del zeta by del zeta equals to 1. Okay, and at zeta equals to 0 means beginning, zeta equals to no, it is not, right? Right. Now what you will do? You have to have the different condition, because this third, eighth is not satisfied, right? It is not satisfied. So from the solution given in the dive, which satisfies the boundary condition 1 and 2 given in the equation 6 and 7, right? So this was the 6 and 7. 6 and 7. Okay. But do not satisfy the boundary condition third equation 8, right? So it is not satisfied. At 0, right, equals to 0 means equals to 3, right? So for that, you are having this 2 pi r into z into q0, right? To the what equals to rho cp t minus t1 vr vz r dr dz, right? When it is for 0 to r, 0 to r, right? Or entirely. So this will be giving you. So if you change this integral using the same non-dimensionalization procedure, and you get uh, it states that the energy entering through the wall over a distance z zeta is same as the difference between the energy leaving through cross section at that zeta and that entering at zeta equals to 0, right? So when you just rearrange these equations and then the expression 9 and the expression 5, when you use, so this was the equation 11, right? And this was 5, and this is 9. When they are used together, now substitute equation 9 and 5. Okay, so then you are getting this 12, and just get this zeta this side and multiply it. You are going to get the expression for psi, right? And this side you can later use for the theta valuation, right? So now final solution for by substituting 13 in equation 9 is this one. And now applying the boundary condition to the constants, and then you are having zeta equals to 0 theta. Give finite, so c1 equals to 0, and then for zeta equals to 1, you are having this one. So once you apply it, you are going to get c0, and then for third boundary condition, once you solve it very carefully, you are going to get c2 also. So finally, this equations and expressions that you have already derived, it gave you this equation in the non-dimensional form, but we need it in the form of temperature. So again, rearranging this dimensionalization that we have used to get temperature T, and we got this one. So this is the final expression, right? So the most important expression out of this entire uh, uh, procedure that we have just done is this one. So what you had is t equals to t1 plus, right, q0 r divided by k, right? And there here you will be having this 4z divided by rho cp z max r square by k plus r by r whole square minus 1 by 4 r by r whole by 4 minus 7 by 24, right? Okay, so this is the one that we want to solve. So this was the overall thing. So on this particular uh, lecture, just let's solve some question. Okay, so this is the expression that we have derived. Okay, okay, 4 mu minus so let's see what we are going to get, right? Wherever the expression profile, this is the profile that I'm talking about. This profile is given, right? So the question says, you just look at this. So we can just set it while reading only. Viscous heating in fully developed laminar Newtonian flow through an infinitely long cylinder tube of radius r equals to 10 centimeter under adiabatic wall condition, right? Described by the temperature profile, right? So the temperature profile is this, okay? Where T1 is 30 in the inlet temperature. Viscosity is given. Okay. Maximum velocity Vz max is what? This one. Okay. 2.73 centimeter per second. Density is this gram per centimeter. Specific heat capacity is this one. And thermal conductivity is this one. What is the temperature at Z equals to this and at midpoint between the center of the tube and the wall of the tube is perfect. Okay. So now what is the temperature at Z equals to 100 centimeter and at midpoint between the center of the tube and wall of the tube. So this temperature difference you are asked, right? So two temperature differences you have to report in this particular question. So how you are going to solve? The basic principle and the concept will be remaining same. And what I want to emphasize here is you just have to know the the steps and the procedure and the physics that is happening over here, right? So that will anyway help you in order to get through this particular problem, right? Let me just see, if you see that so far whatever we have discussed is for the pipe flow with the temperature profile, right? So so if you see this, this is the one. Okay, so now let us solve this one. But before solving this, if you remember these steps that we have just discussed, right? So what all the things that you are having? Let us see. So the temperature T1, we just have a beautiful color right here. Temperature T1 is what? Temperature T1 is equals to 30 degrees, right? And this constant heat flux Q0 is what? 7.9 calorie per meters per second, right? And Cp is equals to 0.2407 calorie per 1 right? So now Cp equals to this 0.2407 into 4.184 for joule into 10 to the power 7, right? So this will give you 1.0070 into 10 to the power 7 ERZ per gram, right? Also, this thermal conductivity equals to 6.60 into 10 to the power minus 5 per second centimeter. Now, if you do this calculation for K, then 6.60 into 10 to the minus 5 into 4.184 into 10 to the 7 equals to 2761.44 per centimeter. Right? Viscosity is given as 1.00 gram per cc, and Vz max is given as 2.73 centimeter per second. Right? So let's see once whether these values are given or not. They are 30, Q0 is 7.9, right? And then this CP is 0.24, this K is 6.0, mu is 1.92, mu is 1, this diesel is 2.73, right? Okay, so just this value of Q0, you see Q0 is this. Uh, okay, so now if you see at R equals to 10 centimeter, at Z equals to 100, what is T? If you get it, you can solve it, right? The expression that you are given with is this. Right? And then if you just look at the values that you are given with, just put these values and do the careful calculations, right? And also at R equals to capital R by 2, it will give you ratio this 2, right? So T equals to what? T1 plus 4, 1.923 into 10 to the minus 4 into 2.73. Wow, divided by 1 into 1.0070 into 10 plus 7 Z by R square plus what? 1.923 into 10 power minus 4 into 2.73 square divided by 2761.44, and this one will come out to be 1.2 whole square minus 1 by 2 into 1 by 2, 4. So this solving, what we will be getting, let me just tell you, it will come out T1 plus 2.0853 into 10 to the square minus 10 Z divided by R square plus 1.1353 into 10 plus 7. Okay. So T will be embossed. Okay, T. Why? Because these are very small, right? You already had this T to be 30, 3 to be 30. So this will give you, this will come out to be approximately equal to this because these quantities are very small. These you are having this 100. So it is very small, right? So option A is correct answer, right? Now moving towards the next question, let me just expand it for you. And these expressions we will be looking at. Okay, this SCUC. So this was the second lecture of the week. So anyway, we will be looking at, but the catalyst problem that was there. But this is easy one. We will be discussing it. Along with that, I will give you the revision of the same. Okay. So consider a spherical catalyst. Okay. So if I can put it here. Yes. So consider a spherical catalyst pellet of radius 2 mm, right? Of thermal conductivity 2.1 into 10 to the power minus 6 calorie per centimeter second degree Celsius, right? Inside the pellet, a chemical reaction is taking place with the rate of the heat generation to be this, right? This heat is lost to the outer surface and then to the surrounding gas stream by convection with the heat transfer coefficient of 7.168 into 10 to the power minus 5, right? Calorie per centimeter square second. Okay. If stream temperature is 30 degrees Celsius, what is the maximum temperature at the center of the catalyst pellet? Useful equation to solve this problem is, what is the maximum temperature at the center of the catalyst pellet, right? This is the center of the catalyst pellet we are asked, and useful equation to solve this is given as T max minus Tz equals to Sc R square by 6K, which is thermal conductivity, 1 minus 4K divided by H 2R divided by H into 2R, and usually if you rearrange it, you are going to get this one, right? So the thing is, how you are going to solve it? Very simple. So let me just brief you a bit before starting it. The calculation that you are going to use, right? So let's revise the second lecture of the week. We have revised the first lecture. So in the second week, we had this heat transfer combined with the chemical reaction, right? So we had in this we had solved three problems of the heat transfer with the chemical reaction, right? So one was this solid sphere, through that there is the transport, uh, and then solid where with porous media there was some transport, and then the third one was the catalyst one, right? So all the three, around 18 slide is there. We will be discussing each very fast, very carefully, right? So heat transfer from a sphere to a stagnant fluid T0 studies heat. So to study heat conduction in a fluid surrounding a sphere in absence of the convection. So there is no convection, and heat conduction in fluid surrounding a sphere. So this conduction you are going to consider a heated sphere of the radius are suspended in the large motionless body of the fluid. Temperature at the surface of the sphere far from the sphere is considered to be t equals to tr and t equals to t infinite. These are the values that they have assumed. Consider the fluid is incompressible Newtonian fluid. Assume that the thermophysical properties are independent of the temperature difference. There is no chemical reaction and gravity is not considered, right? Then what is going to happen? Now, solution is fluid is stagnant first, the surrounding fluid. Thus, there is no need to solve equation of motion. What? The left hand side. So, you will not be having any. So, fluid is stagnant, so equation of motion we are not going to solve. In energy equation, consider only the conduction as a specified in the problem. So, this conduction you are specifically solving. Because in the problem you see this point, assume that the thermophysical properties is independent of physical differences, and you are not considering chemical reaction and gravity in this particular one, but anyway we will be considering chemical reaction in one of the problem in order to see the heat transfer combined with chemical reaction. And then this temperature you have considered this the heat conduction in the fluid surrounding sphere in the absence of convection. So only conduction you are considering. So this is important point to be noted. So if you do that energy equation, so this one is important. Only the conduction as I specified in the problem. So energy equation for this incompressible fluid in the spherical coordinate, you see this is the energy equation. These you can take from the standard books like BSL or this Chabra, right? K upon K square del by del R square del T by del R equals to 0, right? Out of this you see this is transient, then VR, V theta all are 0 because there is no motion, there is no these changes that you are going to consider is the R only. You're not going to see what is happening with respect to this, right? Now just this one. So rearranging you get T equals to minus C1 by R plus at R equals to 0. This should not be infinite, so C1 is 0, right? So and also you see that this at R equals to R equals to TR minus C1 by R equals to C2, and then R equals to infinite, C2 is T infinite, so C2 comes out to be T infinite, and then last one this minus C1 by R equals to TR minus C2, give TR minus C2 equals to this minus C1 by R. R means del T by okay, and this is the from the first one. Just rearrange it, and when you solve it, the temperature distribution that you are going to get is T equals to T infinity minus TR R by R plus T infinity, right? Minus C1 by R, we have calculated this T infinity minus TR by R, so T infinity minus TR by R, T infinity minus TR into R, right? Is divided by smaller minus sign was again and C2. So this you when rearrange you will get this one, right? T minus T infinite. So very important to know this one is this. Let me just fix it here somewhere. T infinite, T minus T infinite divided by TR minus T infinite. Very important. So T minus T infinite divided by T minus T infinite divided by TR minus T. Right. Now look at this. Okay. So rate of heat transfer at the sphere surface due to the conduction, you see this. Okay. At the sample, there is thermal conductivity. So the expression you have used, and then you got heat transfer at the sphere due to the convection will be this one, and then equation equating these two modes of heat transfer, you will get HR by K equals to 1, right? Nusselt number for the case of the heat conduction for the sphere to is Nusselt number equals to 2. Okay, so this was this. So now you got it. Now heat conduction in the spherical cell. It is another problem. In this one, this is spherical cell. So consider a spherical cell with the inner and the outer radius of R1 and R2, right? Make a hole in the cell at the north pole and at the south pole by cutting a conical segment in the region theta 0 to theta 1, and similarly make a hole at the south pole by cutting out the conical segment in the region pi minus theta 1 to pi minus theta 1 is this point, and then pi to pi also here. So you have done it. So surface at theta equals to theta 1 is maintained at a temperature T1, and then at T2, right? What is the temperature profile in the cell? So in the cell, you are going to get temperature. This is the cell. Insulated surface is here. So in the cell, what is the temperature profile you are asked, right? So in this particular, see, first carefully understand this particular geometry. Then only this, this, this you will be going to solve. So let me just open it. Yes, if you see heat conduction in spherical cell one, so this heat conduction in spherical shell, right? So this was what? A sphere and then stagnant fluid. For that you had this equation. So here you had T infinite, here you had PR, this point, and somewhere you want to calculate T, right? Now, so if you look at this one, okay, so this is the point which is theta 1, and this is what? Pi minus theta 1, right? This is pi plus theta 1, or pi you can say. Okay. Now, similarly, in this case, there is no involvement of the fluid, hence only the conduction is the mode of the transport, and then conduction in the theta direction is only taken in this consideration. So, for writing the spherical coordinate energy balance equation for the theta direction, you get this T minus C1 ln tan theta by 2 plus C2. So, these are the condition at theta equals to theta 1, you are having T equals to T1 as given. So C1 and C2 you got one equation, and then at equal to theta 2, then you just need the difference. So T1 minus T2 is this, right? Okay, so this T1 minus T2, when you rearrange, similarly you can write is T minus T2 for the temperature T. Also you can write it, and then T minus T2 divided by T1 minus T2 you can get, right? So another equation that you have just derived is T minus T2 divided by P1 minus T2 is equals to what? Ln tan theta by 2 minus ln tan pi minus theta 1 by 2 divided by ln theta 1 by 2 minus ln tan pi minus theta 1 by 2. Okay, so this if you see, then you get it out, right? So let's keep it here. Now the main topic that we wanted to do is this, this, the combined heat, conduction and reaction energy in spherical catalyst pellets, right? So consider a spherical catalyst pellet of size R. Thermal conductivity of the pellet is K. Inside the pellet, chemical reaction is occurring, right? So due to which the rate of the heat generation is SC. So this you have considered to be constant. This rate of heat generation because of the chemical reaction which is occurring inside the pellet. Pellet is nothing but a circular clumps, ball, sphere kind of thing, which is porous. Okay, so spherical catalyst pellet of size R, thermal conductivity of the pellet is K. Inside the chemical reaction is happening and the rate of heat generation is SC. Heat is lost to the outer surface of the pellet and then to a gas stream by the convective heat transfer, right? And then gas stream uh, at this temperature Tg, convective heat transfer coefficient is H, right? Gas stream at temperature Tg. So gas stream which is there is at temperature Tg, okay? And convective heat transfer coefficient outside is H with the gas, obviously. And then let's assume a rate of heat generation is constant, right? So rate of heat generation you are assuming to be constant. Develop steady state temperature profile and obtain expression for the maximum temperature of the system. So you have to develop the steady state temperature profile. What will be in this particular system given where the catalyst pellet is there and then heat is generated because of the catalytic reaction, and in this one the heat generation because of reaction. You are calculating to be constant SC and there is this gas stream at the temperature Tg, heat transfer coefficient is H. So develop steady state temperature profile and obtain the expression for the maximum temperature in the system. So that's what the maximum temperature has been asked in the question. So if you look at the question that we were discussing is what is the maximum temperature at the center of the catalyst pellet, right? So these values now you understand. We will be looking at the derivation and then we will be just solving it very fast, right? So assumptions are the constraints of the problem is steady state, negligible flow inside the porous sphere, only the conduction mode of heat transfer inside the pellet is considered, and then conduction only in the R direction is happening. So T equals to TR you are considering. So again energy equation in the spherical coordinate you have directly taken it, and in this one you know that there is no motion, so entire left hand side is 0, and also you are not considering anything, the variation of temperature in theta and theta phi, only R you are considering the last line, so that's why these terms go off, only this one you are going to get, right, with SC obviously. So rearranging it and solving for the temperature you will get temperature profile to be SC by K minus of SC by K R square by 6 minus C1 by R plus C2. Now this C1 must be 0 because T cannot be infinite for any value of R. So if R is 0 then T will become infinite. So as per the continuum hypothesis, this one of the quantities flow variables or property will become infinite or not defined at any given point in the domain which we in which the analysis is happening, right? So T equals to SC R square by K6 plus C2. So heat loss to the surrounding would provide required boundary condition to obtain C2, right? So heat loss to the surrounding is at the surface of the sphere, rate of the heat transfer to the conduction is equal to the convection must be equal. So minus K del T by del R at R equals to R, obviously radius of the surface, H equals to TR minus TC, right? Equals to H TR minus TC. So this is equal. So TR minus is the temperature on the surface of the spherical catalyst pellet. So from here, this T is this one. So just you derived it. So derivative comes out to be minus SC by R by 3K. and just this minus a c bar by 3k you equate, put it in the expression to get it related to the heat transfer coefficient, and you will get this equation, equation 5 comes. So equation 3, t equals to this is there. So now t at r equals to r, you got it this one. So t minus, so this c2 equation 2 come out. Yeah? Now if you look at this sc r by 3 ht, this is equation 5, and when you use this tr, you have this in this one, rearrange, we will get c2 to this. And once you got c2, put the c2 here, you will get the expression for t. And now maximum temperature is at the center, so put r equals to 0, then you are going to get the maximum temperature expression, right? So what is the most important uh, finding out of this entire discussion is, let me just put it here, is the expression that comes out at the end. So the second lecture revision is done. So let me just get the final expression over here. So what you got is temperature variation T minus Tg, right? Gas equals to Sc r square by 6k, 1 minus r square by r square, Sc r by Ch, right? And now for maximum temperature, put r equals to 0. What you are going to get? T max minus Tg. Just rearrangement and everything. Okay, so solving the problem, if you see this expression, this was the same expression that you are given with, right? 4k. Okay, so solving this, so in this one it is given that Sc equals to 4.652 into 10 square minus 3 calorie per second centimeter, right? K equals to 2.1 into 10 power minus 6 calorie per second centimeter degree Celsius, right? And H equals to 7.168 into 10 power minus 5 calorie per second centimeter square degree Celsius, right? You are knowing that R equals to 0.2 centimeter with radius, and Tg gas extreme temperature 30 degrees Celsius. The expression that you just derived is this one. So you just put it here. Okay, these two you can cancel out. So this T max minus Pg equals to SCR square divided by 6k, 1 plus 2k by HR, right? When you create this, what you are going to get? T max minus Tg is to 1 4.652 into 10 to minus into 0.2 into 0.2 divided by 6 into 2.1 right. 1 plus 2 into 2.1 into 10 power minus 6 divided by 7.168 into 10 power minus 5 into 2 into 10 power minus 1, right? So what you are going to get is T max minus Tz equals to 14.768 into 10 to the power minus 6 into 10 to the power 6 1 plus 0.29296, right? So this will give T max equals to 30 plus 19.034 equals to 49.09 degrees Celsius, right? So this is the maximum temperature that you are going to get. Okay, so which option you are going to get is, let it be saved. The option 49.09 is first. Okay, so A is so till now the revision is done, and these recordings will be available to you, and you can watch it as per your convenience. And then that's why all the steps and all the calculations are given you step by step, so that things become easy to you, right? Now the next question that is here, again the catalyst related problem is, consider a spherical catalyst pellet of radius 2 mm, right? uh, Iron thermal conductivity is 2.1 into 10 power minus 6 calorie per centimeter second degree Celsius, is maintained in the hot condition at the 100 degree Celsius surface. Okay, temperature. This heat is lost to the surrounding stagnant gas, which is at the 30 degree Celsius by conduction. What is the temperature in degree Celsius at the distance 10 mm from the center of the catalyst pellet, right? So this is another problem that is asked here. So if you remember the way that we have derived spherical catalyst pellet of radius 2 mm when thermal conductivity is given, okay, is maintained. So here there is no such generation kind of thing is given over here. So you may have seen that we have just derived this one. This, stagnant fluid in tin flat. So that case is very much similar to the one which is here. Okay. So what I'm saying is, this case, if you remember, then you can easily get it through, right? Let's just do the calculations which is required. So T minus T alpha divided by T r minus T alpha equals to r by alpha. This was for a sphere in the stagnant fluid, right? So it is similar to that. Spherical catalyst pellet, this is the thermal conductivity, this maintained at the hot condition at the surface of the heat is lost. Stagnant gas, which is important, is at 30 degrees Celsius by the conduction. So only conduction is the mode. So the following equation can be used right? So T minus 30 divided by 100 minus 30 is to 0.2. What they have asked is at the distance 10 mm from the center of the catalyst. What is this? 10 mm from the center of the catalyst. You have to find the temperature, right? So once you do this, what you are going to get is T equals to 30 plus 70 into 0.2 equals to 44 degrees Celsius, right? This is the answer. So this is the third question, this is the answer, right? And the now fourth question that we are going to solve is this one. Consider a spherical catalyst pellet of radius 2 mm is maintained in hot condition at 100 degrees Celsius temperature. This heat is lost to the stagnant gas, which is at 30 degrees Celsius by conduction, right? Then what is the value of Nusselt number they are asking? So you know this. We have discussed today that the Nusselt number of sphere is in an unbounded. So let's write Nusselt. So this one you got, right? This one was 44 degrees Celsius. So B is correct, right? And here it is Nusselt number of sphere in unbounded Newtonian. Wait, is 2 if only conduction is the mode of heat transfer, right? So this we have discussed today. If you want me to put it here, let me just see which slide it was there. I will be just keeping that slide over there. Okay. So this slide, if you remember, this is slipping tool I am searching for. So let's do this. Okay, so this is this. Save. Okay, so let's see the next one, which is fifth. Okay, very important question, because this was the respiration transpiration coolant, right, problem, and this is the part of our last lecture of the week. Okay, so most of the problem now we are going to see is around the important topic that we have discussed in this particular week, the transpiration cooling. Very simple, similar to the same steps that we have already done till now. We will be considering just here is this uh, the, the steps are a bit tricky to implement because of the geometry, right? Anyway, you are having these equations, so that's what I'm saying is if the, you are conceptually sound, you know how the things have to be handled, then there will be no problem at all, right? So let's see. So these four questions we will be going to solve. and then meanwhile we will be revising the last week of this, which is this transpiration cooling, right? So we have seen the definition of the transpiration cooling. Okay, so these four questions we will be solving around this. So let's again take. So we started with the definition of this transpiration. So you remember we in this particular course this non-Newtonian fluids are mostly considered for this transport phenomena studies. But in today's week, in this week, we have not taken any non-Newtonian fluid. What to say? Mostly wherever we have included this thermal, but in the incoming week we will be definitely looking at. But these are the main commonly generalized Newtonian fluids that we discuss: Newtonian fluid, pseudoplastic, dilatant, non-plastic, then this pseudoplastic. Okay, so now this was the thing that I wanted to keep it there. Okay, so let me just take the last slide, then things will become easy to do. Okay, okay, so transpiration cooling. So this transpiration cooling is, as we have just discussed few in the beginning, that this transpiration cooling is an advanced thermodynamic technique. Here, the basic principle is with this method is this latent heat effects, which this utilizes to give the cooling effect, right? And in this one, it is used to protect the structure, wall or porous media from extreme heat by moving a coolant. And these coolant are sometimes liquid and gases. Okay, and the wall may be of porous material. Okay, and this liquid, these coolants can be anything, something called air, nitrogen, or water. And the application of this cooling mechanism, which is this transpiration cooling, is in aerospace, jet engines, and this nuclear reactors. So these are three most frequent places where it is used. Now, if you see this 28 slides, very important. We will be looking at these along with the questions in between, right? So why can't you solve the questions first? After understanding the system, we will be solving the question, right? Then the physical sense of the entire cooling phenomena will be understood. So we will understand the system, and then this slide is very important, the slide 2, because here you will be understanding the system. Okay, and then we will be implementing it to the problem in hand, right? So and this particular system is also important if you actually want it. So this particular image should be with you when you are going to see the questions, right? So let me just put it here, new slide, because this actually tells you what is this lambda, what is this r, where is this T1 temperature is, where is this T lambda temperature is, what is the air in, from where it is coming, from where to where flow is happening, right? And this will give you a sort of understanding in terms of appreciating the problem and catching up the last four problems that we will be solving in this half an hour, along with the discussions that we are going to make, right? So a system with two concentric porous spherical cells, right? These are porous, these cells are porous, this outer cell and inner cell, these are porous, right? Okay, so let me just see. These are porous, and then they are spherical cells. Okay, so it is just 2D map of that cells of radii lambda r, right? Lambda r is this one, and capital R is this one. Obviously, this lambda is smaller than 1, right? So, inner surface of the outer cell is at the temperature T1. The outer cell's inner temperature is T1. Inner cell's outer temperature is T2. Okay, so outer surface of the inner cell is temperature T lambda, right? Dry air at the temperature T lambda, right, is blown, and that's why it is at T lambda, I think, is blown outward radially from the inner cells. So here how you are putting it through this narrow gap into intervening space. This is the intervening space between this and this, between this and this. What I'm saying is this is your intervening space. This is space, right? This is space. This region is what? Intervening space, right? And you know that lambda is less than 1. Okay. Inner space is cooled by mean of a refrigerant coil to maintain the temperature T lambda. Here it is maintained at T lambda. It is cooled through this refrigeration system. Okay. What is the rate of heat removal from the inner sphere? From the inner sphere, how the heat is removed to what rate? As the function of the mass flow rate of the gas. Okay. Assume we study laminar flow and low gas velocity. So gas velocity is low. Important assumptions are what? Gas velocity is low, laminar steady. Okay. Steady, laminar, low gas velocity. Very important. These 4 questions will clear up this entire lecture, right? Whomsoever have struggled in this particular lecture, they will be finding it very easy after going through this particular session, right? So what I'm saying is it is very important for you to attend this live sessions, because here we are solving the question, and then while solving the questions we are revising the entire content of the week, right? So it is giving you dual uh, 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 explanation, right? So it is giving you dual revision. You are revising the whole content within the span of 2 hours. At the same time you are connecting those content with the problem, and when you are solving the problem you are having some values associated with different parameters. For example, I am telling you the temperature of the wall is this, or the loss because of the reaction is this. Okay, heat loss because of the reaction is this. So these values, whatever I am telling you, these are some typical values have been taken, which are experimental or somewhat real, right? So it gives you a sense of reality while learning the subject. Okay, so if you see this, what I'm saying is this one. Yes, if you see this, uh, this entire expressions, right? So now you understand. Let us solve the questions, and once we solve the question we will thoroughly revise it, right? So these are the, again you had these spherical coordinates have been taken, and since the low gas velocity is there, so the velocity you have taken it to be vr r, and it is very low, and radially it is going out. Temperature as a function of Tr you are considering, and pressure as a function of Pr. So here too you are deriving 3 profiles: temperature, pressure, and velocity, right? Equation of continuity you have used here. You know that there is no variation because of the theta and phi, only the variation because of the r. You have considered it to be steady. So based on that you had this 1 by r square d by dr r square rho vr and through this you will get that r square rho vr is constant, right? And also let wr, very important, be the radial mass flow rate of the gas, right? So, so this WR, omega R, is given as rho VR, and what is the area? 4 pi R square. And this is the element that you have taken. Here you have taken an element of at R distance. That's what the radius which is taken. So here R square rho VR equals to omega R. This. So now you know that this particular, from this particular equation and this particular equation, you will know that C is omega R by 4, right? Now, omega r by 4 pi, Vr is what? You can calculate Vr accordingly, right? So, theta component of equation of motion will give you that your pressure is not the function of theta, right? And the pressure is not the function of phi. It will be given by phi component of the equation of motion, because you are solving the entire thing in the spherical coordinate, right? In the r component of equation of motion, what it is going to give you, you know that these terms will be going to zero, because you are not considering any variation in the theta and phi, and you are not having this steady state. And at the same time, what you are having is this there is no variation in theta and phi, right? So theta phi, these will be going out, but this will exist because there is this finite Vr. So this rho Vr del Vr by r equals to minus del P by del r. This will be existing plus this. So you know that P is not the function of theta and phi, but from here you can see that it is function of r, right? So how you are going to solve this equation 2 is the major challenge right now. So once you see that this equation 2, when you integrate it, okay, from PR to so from PR to pressure at any R to pressure at radii R, okay. And this term, why you have taken this term to be 0? Because through the continuity you got it. Through the continuity you have derived it, that this 1 by r square d by dr, r square rho vr is 0. 1 by r d by dr, r square rho vr, rho is constant, is 0. So only del p r you are adding. And once you do this, you will be getting this rho vr square by 2 r to r, er minus vr. Solving this, what you are going to get is vr is this, right? R square rho vr equals to this. So this is this another way. Also you had this, and now you can connect it, right? You can put this vr in terms of rho r, which is, what is the rho r? You had this mass flow rate of the gas. So radial mass flow rate of the gas, you are having this omega r, right? So once you put this omega r here, what you are going to get is the main expression over here, omega r square. So very important expression. Let me just prompt it out. So some few expressions that we have just derived is very important in terms of understanding the entire thing over here, right? So first is whatever relationship we have derived of omega r and this here, right? Equation 1, important equation 1 is this omega r divided by 4 pi equals to what? R square rho vr. Okay. And afterwards, now whatever equation you have derived in terms of pressure drop, right? So equation 2, which is important, is omega r square divided by 32. Let's expand it. 32 pi square rho r square, right? 1 minus r by r power 4, okay, equals to pr minus pr, right? So if you see now, was the energy equation, because pressure you got, velocity you got, not temperature. So this is the full equation of temperature energy balance for the spherical coordinate system. Uh, so you see that in this one, everything v theta, v phi containing terms, or del by del theta, del by del phi will go out, but del t by del r, del t by del r, v r, they will be existing. So these two terms will be here, right? And we want to solve this. Okay, so we know that Vr equals to omega r 4 pi r square r. So when we put it here, okay, then we will have this particular del t by del r we can rearrange from here, right? And this del t by del r that is here, you know that this r0 del t by dr equals to d by dr r square dt by dr, right? Why from the del to dy you came up? Because you just see this, okay, it is only having the dependency on r, so this other partial other independent variable phi and theta is omitted, so only r is there, so that's why this uh, del is changing to d. And once you solve this, okay, yeah, you just rearrange it and take this omega r cp by 4 pi k to be r0, you will get this equation. So this equation, let r square dt by dr to be ur, and then when you do you solve this for dt by dr, then you will have ur by r square. So also this r0 ur by r square d by dr, here you write this one r square d by ur, okay, r0 dr by r square, okay, so just rearranging it, ur by u. Okay, so once you solve it, you will get this, I mean this u expression, right? rearranging rearranging it u expression, what you are going to get is the dt by dr, okay, and this dt by dr comes out to be this, okay, and here the constant c2 is there, okay. Now this exponent of minus c1 you have taken it to be c2, and then you want to solve it, rearrange it. Once you rearrange and do the juggleries, what you are going to get is the final expression of temperature. Okay, so I'm just coming to this very quickly, very fast, because this is the temperature distribution that you are going to get when there is no assumptions involved, right? There is no much assumptions as per the kind of heat and the airflow which is there, right? So what you are having, T minus T1 divided by equation 3. T lambda minus T1 equals to exponent of minus R0 by R minus of exponent of minus R0 exponent of minus R0 by lambda R minus exponent of R0 by R. Okay, so this is that. This is the final temperature distribution. Okay. Now, the rate of heat flow outward because from the inner sphere, if you see. So what I'm saying is, let us look at. So what I'm doing, whatever main expressions I am arriving at, I am just taking it into the slides, right? So the final temperature distribution we got from our main calculations that we were performing here, right? Okay, here taking this r square del t by del r, and here the expression for q is 4 pi lambda square r square, which is lambda inner radius, outer radius of the inner cylinder. Okay, Are you getting my point? Outer radius of the inner cylinder. Okay, this is this. So this, if you see from here, what is the flow of heat you want to calculate? So at this, and this is the required rate of the heat removed by refrigerant, right? So what is that? QR is equals to minus K del T by del R equals to gives Q equals to this. Okay, and you are having this. So once you put it here and solve for Q, then what you are going to get? The expression of Q to be this one. You just put it here. The expression of Q comes out to be what? The Q comes out to be 4 pi K R0 T1 minus T lambda divided by Txp R0 by lambda R 1 minus lambda minus 1. Right. So in the absence of mass flow rate, what will happen if there is no mass flow rate? Only the conduction term in the energy equation would be considered. Equation will reduce to equation 4. So what is the equation 4? Where the conduction term will be only considered. So let me just take you to the equation 4. Very, very important. This is the equation 4. In this one, we started from here. Only the conduction term will come up. These all will get 0. We have considered these, right? This will not be there. So only this will be considered. And in that case, if you solve it, right, then the equation 4 will reduce to this. When you rearrange it, T is coming out to be this. Okay. Boundary condition at R equals to R, T equals to T1. Okay. And at R equals to lambda, T equals to T lambda. You just subtract it. You will get this one. And C4 is this one, right? Now C5 equals to C4 by R using the main equation. Okay. From here. So in that case, if there is no transfer of mass flow rate of the gas, we'll get this final expression, absence of radiant gas flow. So let me just write it. So equation 5 is what? So main equations we have T minus T1 divided by T lambda minus T1 equals to what? 1 by R minus 1 by capital R, right? Divided by 1 by lambda R minus 1 by R, right? Okay, so you look at the problem. So this will give final temperature profile in the absence of radial gas flow, right? So let's see. It is hang now, but anyway we can look at this. Okay, come. Yes. So Temperature profile in the case of no gas flow can also be found as below. So this is the another method of reducing. For a small R0, okay, this e to the power minus R0 R, this will be coming out to be 1 minus R0 by R, and this term to be this one, and this term to be this one. So now substituting this information in the final expression that we had, we get this one, right? This is the another method of deriving it. So what this method tells, how you will derive equation E5 using E4 using what, using E3, how you can derive this E5, right? So that's what it is. Okay, so in the absence of radial flow gas, we can also define this heat removal as Q0. And similarly, the expressions have been used. Let me just put it here, because why I am putting all the expressions over there, it then you will know what is the important thing. So then there is no, and in this case Q0 is what, 4 k lambda r T1 minus T lambda divided by 1 minus lambda. So that's what is the main derivation, right? Now, if the limit of mass flow rate of the gas is 0, R0 equals to 0, then the rate of the heat removal is this one. So mass flow rate of the gas is 0, then you will have this one. Okay, that's what we have to see. Final fraction reduction in the heat removal as a result of this transpiration of the gas is then what, this one. So very important expressions. So this what, fractional reduction in heat removal as a result of transpiration of gas in gas is what, Q0, which is Q0 afterwards, and Q was initial one divided by Q0 was to what, 1 minus okay. So and this is what, R0 1 minus lambda divided by lambda r. You can write it as omega r Cp cap 1 minus lambda divided by lambda. Okay. So this, if you solve, what you are going to get is dimensionless transpiration rate, right? Very good. So now let us solve these questions very fast, very quickly, because we are having very less time right now, right? But the main thing is we are having very good basis right now, because we have dealt all the theory very carefully, and then that will be anyway helping you to solve very quickly. We are going to solve this around 10 to 15 minutes we will take to solve these 4 questions, right? So consider transpiration cooling system by two cell of sphere with the radial gas mass flow rate. Okay, 10 to the power minus 50, right? Let me just fix it here. The following conditions are equal to 50 micrometer and are equal to 100 micrometer. T1 is what? T1, you know, this lambda 1, you know this, k is this one, right? uh, you are having this one. Okay, so what is the rate of heat transfer at the inner sphere cell? Okay, useful equation is given here. So this particular equation you have to solve. So this is direct formula based question. So what I am saying is the particular expression that you are having is this one. So let's solve this one first. Okay, so when you put the use the following equation as it is given over here. Okay, so then it will give you 4 into 3.14 into 6.5 calorie per centimeter into 5 degrees Celsius into 100 into 10 to the minus 4 centimeter into 200 degrees Celsius divided by 1 minus 0.2. So what you are going to Q0 equals 1.9248 into 10 to the power 6 into 10 to the power minus 5 into 10 to the power minus 4. What it will give you 1.9248 into 10 to the minus 3 calorie per second, right? This is Q0, right? Very good. So this is Q0 that you have got. Okay, this was the expression that we used over here, right? In the absence of radial gas flow rate. The question before, so this you know that 1.92, this D is correct. D is correct. Right now, this particular question, if you see here, what it says is consider transpiration cooling system by the two cell of the sphere with the radius of the gas as given here. Okay. Okay. What is the rate here? So we have solved this one. What is the rate of removal? Is this here the without radial? So this is important. Without radial flow we have solved, and here there is this with radial. I think with radial flow. So this is very important. So as we have seen this, let me just take the question over here. Very quickly, let us solve it. Okay. So lambda equals to what? Inner radii divided by outer radii of sphere. 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 Right? And R0 is what? Omega Cp cap divided by 4 pi k. So when you do this Q0, you got it, right? Just put the values. So this Q0 equals to what? 10 to the minus 5 G per second into 0.25 calorie per gram degree Celsius into 200 degrees Celsius into 0.2 divided by what? What? Exponent of very important terms. 10 minus 5 gram per second into 0.25 calorie per gram degree Celsius divided by 4 pi 6.13 into 10 to the minus 5 into 100 into 10 to the minus 6. Okay. So 1 minus 5 minus 1. Okay. So once you solve it, I'm just going to write all the steps. So Q0 is what? 100 into 10 power minus 6 divided by exponent of 0.25 into 10 power minus 5 divided by 77.0251 into 10 power minus 9. 1 minus 0.2 minus 1. Right? Once you do this, Q0 is what? 500 into 10 power minus 6 divided by exponent of 0.5976 into 10 power minus 3 divided by 10 power minus 4 minus 1. Once you do this, 100 into 10 power minus 6 divided by exponent of 25.976 minus 1. So it will give you 5.18 into 10 power minus 60 calorie per second. Okay. So let's see this. Okay, so let me just see where it is. After that, I have some here. Okay, so this is this, and then this is this. So this is 5.18. 5.18. So this is the closest one. This should be 5.18. Okay. Now let us move to the next question. Calculate temperature in degrees Celsius at the R equals to 30 micrometer point in between two cells of the sphere used for the transpiration cooling purpose for radial gas mass flow rate at 10 to the power minus 5 g per second. For the following condition, R equals to 500 micrometer, and then okay, let's see. And then this is here. Okay, very important. Okay, so again you are equation to solve this equation here. Calculate the temperature at this. This is the question. Calculate the temperature as R equals to 300 micrometer. So let us solve it. R equals to 300 micrometer. Okay, so when you solve it here, so this value will come out to be what? 0.185, right? And then T equals to T1 plus T lambda minus into 0.185. So this will give you 300 plus 200 into 0.185. It will give you 327 degrees Celsius. Okay, and this R0 and R, you know. So they asked you at R equals to what? R equals to 300. And this capital R, you know, this is what? 500. Right? And this R0 you have to calculate, right? But this R0 you know very well. You know, this R0 you know. This R0 omega R Cp cap divided by 4 pi k. Omega R Cp cap. So in the case of omega, right? But in the case of this, R0 is what? R0 is 300, this is 500. So all the values you are given. Okay. Now this R0 you have to calculate and then accordingly you solve this particular. So, so 337, you just check it. The answer is 337 degrees Celsius, right? So A is correct answer. And now the last question is this one. Calculate the temperature in degrees Celsius at R equals to 300 point this one. T1 is this, this. So now the different equation you are using, but you are solving for the same thing, right? What I'm saying is these are very simple. Everything we have discussed in today's class. What I'm doing is this value in this one you will get this to be 0.166 and t should t1 plus t lambda minus t1 into 0.166. So t equals to 300 plus 100 into 0.166. So t equals to 330. Okay, so this is the option. Okay, so now you see that we have already come up with this, and I hope this lecture helped you. Thank you so much. Thank you.